Hello everyone, I hope you are doing well. In this video, we are going to solve problem 4 from chapter 6 of Fundamentals of Statistical and Thermal Physics by Reif. This is the book name. So let's see the problem statement and we will dive directly into the solution. If you are looking for the solutions of other problems from this book, then you can visit the Statistical Mechanics Reif playlist. I have added all those solutions in that playlist. So let's quickly get started with this problem. The statement says a sample of mineral oil is placed in an external magnetic field. So the first few lines are describing our system, and after the first few lines we'll be introduced into the main part of the question, which will tell us that what we are gonna find out in this problem. Okay, so first we have some long description of our system, and they say we have some mineral oil and we have placed it in an external magnetic field. Each proton has spin half and a magnetic moment mu. It can therefore have two possible energies, E equals minus plus mu h, corresponding to the two possible orientations of its spin. Here the main thing that we have noticed is that we have a system that has two possible kind of energies, which is minus mu h or plus mu h, corresponding to the two different possible orientations of its spin. Alright, so we have two possible energies. What happens next is an applied radio frequency field can induce transitions between these two energy levels if its frequency satisfies the Bohr condition h mu equals 2 mu h. Okay, let me clarify you first that what our system looks like. Alright, then we can proceed with the problem statement. And basically what they are saying is that we have a sample of mineral oil. Let's say this is a sample of mineral oil and it is placed in an external magnetic field H, and this mineral oil has many protons in it. Let's say each hole is representing a proton in it. Now proton has a spin half, and when that sample is placed inside an external magnetic field, the proton could have two possible energies. One is the lower energy state and the other is the higher energy state. The lower energy state is minus mu h. Since it's a negative energy, it is a lower energy state, and another is plus mu h as it is given in the question. It has two possible energies. One is this negative energy and the second is this positive energy. Now the protons out of all, they could be in low energy state or high energy state. Now what happens is that if a proton in low energy state absorbs a photon of energy h mu equals 2 mu h, then it can transition to a higher energy state. Okay, this is something they are saying, that a low energy state proton can make transition to a higher energy state by absorbing this photon. Why this photon? Because the difference in the energy level of these two is like E2 minus E1 is the difference in the energies, which is mu h minus into minus mu h. Okay, that is equals to mu h plus mu h and equals 2 mu h. That is why this amount of energy has to be absorbed by a lower energy proton to transition to a high energy state. Okay, so let's again read the statement. If we have two energies here, okay, an applied radio frequency field can induce transitions between these two energy levels if its frequency satisfies the Bohr condition. Like if we apply a radio frequency field on that system of a mineral oil sample, if we apply a radio frequency field whose frequency is such that they satisfy this condition, like the energy is 2 mu h, then the transition can happen from lower energy state to a higher energy state. If we bombard a radio frequency means photons of energy 2 mu h, then this energy will be absorbed by these protons and they will transition to a higher energy state. That is something that they are saying actually. Now, the power absorbed from this radiation field is then proportional to the difference in the number of nuclei in these two energy levels. So, how much power will be absorbed by the sample? It will be proportional to the difference in the number of nuclei in these two energy levels. Assume that the protons in the mineral oil are in thermal equilibrium at a temperature which is so high that mu h is very less than kT. How does the power absorbed depend on the temperature of the sample? So, here is the main question. And what we have to do in this problem, how does the power absorbed depend on the temperature of the sample? So we need to find out the relation between power absorbed power in this process with the temperature of the sample. All right, so this is the main thing that we need to calculate, and we are given with some supporting information that will help us to solve this problem. And that supporting information is that the power absorbed is proportional to the difference in the number of nuclei in these two energy levels. This is what we have to do and will bring us to the solution and the thing that we need to calculate. Okay, this is the central information, and there is one approximation that is given, which is the higher temperature limit. As we can see here, the temperature is so high that mu h is really less than kT. Sometimes these approximations are applicable and sometimes not, but in this problem this approximation will help us to narrow down the situation into a really easy relation between power absorbed and temperature of the sample. We'll see it later. Let's quickly get started as we have understood the situation, and now it's the time to actually solve the problem. Understanding what the problem is half the solution actually. Okay, so that is why I focused a lot on making you people understand that what this whole statement is. The solution is really simple. Let's start. Let E1 equals minus mu h and E2 equals plus mu h. These are the two possible energies. Let P1 be the probability of protons, or you can say nuclei, to be in E1 energy state, and P to be the probability of protons to be in E2 energy state. So let's write down the probabilities. We have P1 equals e to the power minus E1 by kT divided by Z. This is the probability in first energy state, and P2 equals e to the power minus E2 by kT divided by Z. Alright, let's calculate Z. This is 1 and this is 2. Let's calculate Z separately and then we'll directly put the values. Here Z is the partition function and it is given by e to the power minus E1 by kT plus e to the power minus E2 by kT. This is simply the partition function, and we can put the values directly here. Minus into E1 is minus mu h by kT plus e to the power minus E2 is mu h by kT. This is minus minus plus, so e to the power plus mu h by kT plus e to the power minus mu h by kT. This is the partition function. Now let's put this into 1 and 2, putting into 1 and 2. Alright, so let's put in P1 would be equals to e to the power minus, in place of E1 I'm writing minus mu h as well, divided by kT, and we have Z in denominator, which is e to the power mu h by kT plus e to the power minus mu h by kT. 1 equals e to the power minus minus becomes plus mu h by kT divided by e to the power mu h by kT plus e to the power minus mu h by kT. Call it as equation number 3. Now let's put in P2. P2 equals e to the power minus E2 by kT divided by e to the power mu h by kT plus e to the power minus mu h by kT. We'll put the value of E2 here, which is mu h simply. So this is the situation. This is P2. Let's call it as 4. Now we have seen that the power absorbed is proportional to the difference in the number of nuclei. These are only probabilities. They are not showing the number of nuclei. To find out the number of nuclei in each of these states, what we have to do is simply multiply capital N with these probabilities. So let capital N be the number of nuclei, be the total number of nuclei in the sample. Nuclei in the sample. Then number of nuclei in E1 state would be let's say we call it at n1, which are the number of nuclei in E1 state, equals capital N multiplied by P1. Okay, this is the number of nuclei. If we multiply the total number of nuclei with the probability of nuclei to be in E1 state, then it will give us the number of nuclei in E1 state. So capital N will be multiplied by e to the power mu h by kt, as from 3, e to the power minus mu plus mu h by kt minus mu h by kt. So this is n1. Similarly, number of nuclei in E2 states will be capital N2 equals NP2. This is equals to N E minus mu h by kt, mu h by kt plus e to the power minus mu h by kt. Okay, and the power absorbed is proportional to the difference in the number of nuclei in these states. So we'll find out the difference now. N1 minus N2 mod, because difference could be positive or negative, we are just interested in positive values difference. So n e to the power minus mu h, plus mu h by kt, e to the power mu h by kt plus e to the power minus mu h by kt, minus, we have this term now, plus e to the power minus mu h by kt. Taking capital N common, and LCM will be e to the power mu h by kt, because the denominator is same in both the values. The denominator is z, which is this. We have e to the power mu h by kt minus e to the power minus mu h by kt. Okay, now we'll use the approximation, which is the higher temperature limit here, which will help us to simplify this a lot more. And for that purpose, what we will do is, since kt, since mu h is really less than, since mu h is really less than kbt, so we can use this approximation when we have this situation like e to the power mu h by kt would be equals to 1 plus mu h by kt. If it is plus here, then there will be plus here. If it is minus here, then it will be minus here. Okay, so since we have both of these, so let's insert these values right into this equation, right into this expression. In place of e to the power mu h by kt, we'll write 1 plus mu h by kt. In place of e to the power minus mu h by kt, we'll write 1 minus 1 minus. There will be no minus with 1, only minus here. Okay, 1 minus mu h by kt in place of this. Okay, so let's do that. N1 minus N2 mod equals capital N into 1 plus mu h by kt minus, then we'll use bracket because it's needed, 1 minus mu h by kt divided by, we have e to the power plus mu h by kt, so we'll write 1 plus mu h by kt, then we have plus sign, and we have 1 minus mu h by kt. Let's simplify it. This is plus and this is minus, cancels out. 1 plus mu h by kt, this negative sign multiplies inside, it's minus 1, and it will become plus mu h by kt divided by, it's 1 plus 1, which gives 2. Capital N equals this, and this cancels out, and we have 2 mu h by kt in the numerator, and this 2 could be written outside. This 2 and 2 cancels out, and we have n mu h by kt. As we have reached to a really simple expression now, let capital P be the power absorbed, since P is proportional to the difference in the number of nuclei in both of these states, which is this. So P is proportional to n mu h by kt as well, because this is equals to this. And since again we wanted relation between power and temperature, so we can see that we can take all other things as constant, which are actually constant. Capital N is constant for a given sample, mu is constant, h is constant, kb, which is Boltzmann constant, is constant. So we are left with 1 over t. and power absorbed is inversely proportional to the temperature. Alright, this is the relation between the power absorbed and the temperature of the sample, and that is something that we needed to calculate. Hence, we can write P power absorbed is inversely proportional to the temperature of the sample, which means greater the temperature of the sample, lesser power will be absorbed, and vice versa. Alright, this is the end of the solution, and we'll meet you in the next one. I hope you like it, share it, and please subscribe it. Goodbye.